Hello, everybody, and welcome to the virtual seminar series on Bayesian decision making and uncertainty. Uh, I'm Alex Turenin, one of the hosts for the seminar series based at Cornell, and I'd like to thank my fellow organizers, Renato Berlingeri, Natalie Maus, and Si Wang for their work in helping put the seminar series together. And we're going to get started shortly, just after a few organizational announcement. The first one is that you can find the schedule for future seminars on our website, which is gp-seminar-series.github.io. And yeah, so check that out. You can join the seminars via Zoom as long as you register on the Google group to get emails with the seminar links, which can be done on the website, or you can always watch us via YouTube, which doesn't require any registration. If you're joining on Zoom, you can ask questions during the seminar in the chat, and the speaker can choose to pause and answer questions during the talk or to hold questions on the end, depending on their preferences. And with that said, it is my great pleasure to introduce Richard Song, who will give today's seminar. Thank you so much. The floor is yours.
Okay, hi everyone. Let me share screen. Yes. Yeah. So hi everyone. Thanks for giving me the chance to give this talk. I'm currently at Google DeepMind, working a lot in AutoML, but also recently LLM reasoning. So today's talk is gonna have more of a flavor of like LLMs, and I'll explain why and like all the nuances and its relationships to the AutoML and Bayesian learning community. But let's just start off. Let's just begin. By the way, like I'll have like intermediate slides where I can answer people's questions in the meantime. Okay. So yeah. So the title of today's talk is text to text. Both internally at Google and externally at academia, right? So like I've had a lot of collaborations with people inside dealing with like Bayesian optimization and how it's used in things like ML efficiency, things like that. But as I've also had a lot of like discussions and like even co-authorships with people in Sakana AI or in academia like UCLA, Stanford, CMU. So yeah, to begin, basically, I want to talk about like what's happened so far, right? So we can say that 2022 to 2023 was the year of ChatGPT, and this was great for VCs, startups, governments, and employees, right? And this is where sort of like AI became kind of mainstream, and also where LLMs also became kind of mainstream. But I'd actually argue that this was actually one of the worst years for non-LLM research, right? Especially like this was especially a confusing time for people in Bayesian optimization and AutoML because there were a lot of lingering questions such as, okay, how do we remain relevant to LLMs, right? Should we even care at all about LLMs? And also, like it's interesting how like a lot of the LLM topics aren't exactly like mainstream or super relevant, and directly super relevant to AutoML researchers. And so there have been quite a few like different like responses to this, right? So for one example, I think like the AutoML conference, right, most recent AutoML conference, like basically I don't think there are a lot of papers there regarding LLMs, right? I think most of the papers there have been very like more traditional, right? Like things like neural architecture search, tabular regression, things like that. And you can sort of understand why, right? For example, like um, those topics are still remain as like rigorous, and since they're very domain specific, you can sort of like do a lot of analysis on those, right? It's not as generic as an LM. But also other people have actually taken this to be they embraced it a lot more, right? So for example, Sakana AI, right, released these papers like AI Scientist, where the evaluation sometimes can be very like subjective, and also from a point of view of like a more rigorous researcher, like there are a lot of like agentic kind of frameworks, and like sometimes it can look a little hacky, right? And also like they're basically using an LLM for the entire like end-to-end machine learning pipeline in a sense, right? Or some other communities have actually taken this into more like an in-between kind of thing, where right, for example, the field of prompt optimization popped out, where it's really just the same thing as Bayesian optimization and black box optimization, but the search space now is in strings. But there's still a lot of principled studies on this, right? You can still define the notion of like sample complexity and things like that, right? Before I begin, go on. Are there any questions? Okay, cool. So one argument I have for why like this kind of like these issues, you can say issues, are kind of happening is because of human feedback. So I like to give off this like first slide, basically trying to say that like right, is this useful, right? Like if we prompt Gemini or ChatGPT to write a poem about like pizza, right? It can probably actually do that very well because specifically because it's trained very well to do these kinds of things. But you got to wonder if like, are these tasks and abilities actually useful, right? Sam Altman himself didn't even think so, right? In I think one of these Lex Friedman podcasts. And so a big reason for this is because what I call reward modeling. So for example, um, like I think everybody might have seen this figure, right? It like outlines the paradigm of RL fine tuning, where we have a base uh, LLM checkpoint, and then it's going to perform reinforcement learning fine tuning on what's called a reward model, right? And so this reward model, generally speaking, is like an imitator of humans, right? That's why they call it reinforcement learning from human feedback, right? So in here, like the humans dictate subjective ratings, such as creativity and personality, safety, and also the human verifiable factuality. So this is great for human interaction, like writing prose, like poetries or essays, conversations, and also in general, like likability and human values. But actually, I would argue that this is incredibly poor for experiment prediction, business metrics, and forecasting, right? And another, as an aside, right, like a lot of these metrics also are very coarse. So, for example, people have these like ask the humans to rate some like output of an LLM, but the scores are very coarse. Like they're just like integers between 1 through 5. They're like kind of like Yelp stars or something, right? And from the perspective of like a Bayesian, someone who works in the Bayesian field, that's like really, I'm sure that this would annoy them. So recently, however, the field has really gone more towards like ground truth rewards, right? And it's not exactly like like high precision numeric outputs. It's still like did you get this question correct or wrong, or false kind of feedback. But people are seeing the powers of this, right? Like once you do this RL fine tuning on top of like grounded rewards, the LLMs became like superhuman reasoners in some sense, right? And so the question is also like, what happens next after this? After we've exhausted all these kinds of like fast, like just basic, textbook questions. So I'd argue that in one case, we might need RL from world feedback. So for example, if we want to have like superhuman machine learning scientists, maybe we need to train on experiment outcome feedback, right? Or if we want like a superhuman chemical designers, maybe we need to train on making chemicals. And just another like random example, like if we're trying to get the LM to like design great planes, right? You might have to train on like making expensive plane designs for checking like which metric is good and so forth. But one issue here is that these rewards are expensive, right? You can't just train a LLM over like for it to like start doing ML experimentation and then wait for like some CFAR 10 training pipeline to actually run, right? That'd be way too expensive. But it's interesting how like other people also do think this. Where, for example, like I'm not associated with this AI safety forum, but I did look at one of the posts, and so basically they said that they predict that in the first half of 2025 we're gonna be really scaling up RL training, right, up to like tens of millions of dollars, up to maybe even $1 billion. And then people also this post also has said like maybe to get to the point where we have like superhuman AI scientists, we need to also train these models on predicting out the outcome of all these like machine learning research experiments, right? And so this is more like a general theme. It's like, how do you get there, right? Um, and so one way perspective to see it is you can see actually these reward models from the AutoML lens, right? So what that means is you can see that reward models are more broadly language model regressors over black box objectives, right? Currently the focus has been mainly on human feedback, but has we should extend it to things like any black box function. So as an example, it can be the outcome of experiments, like I said, or metrics over production systems, or environmental feedback, right? And so actually there are different names for different communities. So for example, the LLM community calls these things like reward models, autorators, verifiers. But the AutoML community, the Bayesian learning community, you can also call these things as regression, performance prediction circuits, right? So as a concrete example, like what are we going to do with language models for regression? So for example, suppose that I want to predict out the outcome of some experiment given some hyperparameters, right? So in my prompt, I will say like, I'm training a ResNet on C410 and it has some certain batch size, learning rate, et cetera, hyperparameters, right? And the goal is to predict out the accuracy after you train this model. And so, right, this is regression and experimental design where your X are kind of like tabular hyperparameters, where, for example, you have a floating point that's the learning rate, a category such as like, what optimizer you're using, or integer input, which is like the number of layers or something of your model, right? And the Y output is like your scalar metric, your accuracy. So if we manage to solve this problem, right, then there are many benefits. So for the LLM community, you now have reward models being able to simulate systems or nature. And also you have a lot more precise word modeling, right? It'd be nice if like the language models could actually output a very high precision numeric scores rather than these like, 1 to 5 star Yelp reviews or something, right? And also like for the AutoML and Bayesian community, right? You now can have flexible text-based regression. And also since these language models don't really care about like constraints and a notion of like feature engineering, you can actually do a lot of multitask and meta learning. And right, ultimately, these language models are very easy and scalable to use. Right, you just train a ton of data, and you don't need to do that much, do too many other things. And so, right, how this relates to current researchers, for example, right, people have been studying things like test time compute recently, right, where a lot of times, like given LLM outputs, you want to use some sort of verifier to say like filter out some of the incorrect answers, right? Well, if we had a regressor for like predicting out real world outcomes, right, we can sort of have a world verifier as well. And this is important for things like right, black box optimization in very exotic domains now, right? Like, for example, there have been a lot of papers which try to do evolutionary search over code. And the problem here, right, is that evolutionary search can sometimes be pretty sample inefficient because a lot of times it's just like a LLM doing random mutations on some piece of code, right? If we can have a Bayesian optimization variant of this using a regressor, that'd be much more efficient, right? So this is an important topic overall. Is like how do you do regression with LLMs, basically? And before I continue, are there any questions?
Just a brief note for participants, which is you should be able to ask questions if you'd like to at any point by writing them into the chat. If for some reason that's not working and you need a way to contact us, then you can either try the raise your hand option or, worst case, send me an email or to any of the other organizers and we'll get the technical working. But it should be possible to ask questions by writing in the chat.
Okay. I guess I can continue. Yeah, so basically back in roughly like 2024, 2023-ish, like we had an intern, Oscar Lee, who was a great intern, try this out actually. So we had a very first prototype, and this was actually before like things like Gemini or anything like that came out. So it was actually on the first generation of language models that Google had, which are like called T5, basically, right? And yeah, so just as an aside, right? Like another thing, the goal of this, right, is we don't want to really change too much about LLMs or like how you train LLMs in general, we want it to be simple and scalable, right? And so like uh, if you have that, then you can actually have a very general purpose regressor method that can just like simply take in any format, right? And so the main punchline I want to talk about here, it really is just um, if you have X, Y pairs from any regression task, let's just convert them into text. Then you perform supervised fine tuning over the prompt and target. So like prompt is your X, target is your Y, and that's it, right? It's simple and scalable, and it actually will work. Like like if you get wanted to just like get any if you learn anything from this like talk, right? This is the main punchline. And it's important that X actually can be anything, right? So it can be actually tabular data, code, um, like JSON formats of anything like you see normally in software engineering, or things like computation graphs. It can just literally be anything. And it doesn't even have to be text, right? A lot of language models these days are now multimodal. So the X can actually be possibly figures later down the line as well. Well, at least on tabular regression, right? The most basic and well-studied task. I'm going to talk about like how we do this. So what we're going to do is, right, we have a prompt and a response, and we're going to only compute the loss on the response, right? And so in tabular regression, you basically have like a task, and it has like X, Y pairs, and like you can also sort of define what the task is using this metadata, right? So when we serialize the X, right, we represent it as natural language in JSON, and more importantly, it's represented as raw values, and there is no normalization required, right? So, for example, like this batch size number, right? It's 128. We don't actually need to normalize that at all, and so we also don't need to know these like the input space bounds at all, right? And so, like this is a very absolute kind of format. For the M, right, this metadata kind of like uh, string. What we also do is like natural language, and the idea here is like you can sort of shove in anything, right? And it basically conditions the distribution to say tell the model like what task it's on, right? And so, for example, like uh, I'm gonna get to this later, but like we use like hyperparameter tuning data, so it actually contains people's like usernames, objective function names, titles, whatever. And also, here's another important thing is the y, how are we going to represent the y values, right? And so when we started off, basically we wanted to simplify this down and say like, let's represent every y value as just like a fixed length custom token so that we have full control over like how it's represented, right? So basically what we do is we represent a y value in terms of like the sign, a mantissa, and an exponent. Right. So for example, in this case, if we wanted to serialize the number 1.23, that's how we do it, right? So it's like a plus and then 123, and then there's some exponent token representing like what's the power of 10 being applied here. And right, like I said, this is important because it's in absolute format. We don't need to do any normalization on this, right? This is again, like I said again, this is one of the first cases where we don't need normalization on any regression model. And yeah, so like at inference time, you can force the model to output like an actual legitimate number by doing restricted decoding, right? So what that means is basically like at every position, you can always like mask out the wrong tokens and only like masking the right tokens. So it's always guaranteed that when you do decoding with this model, it always outputs a valid numeric representation, right? Yeah, like I said, it's on raw values and no normalization. And so, yeah, like I said, this is a very big regression paradigm change where your X no longer needs to know anything about bounds or it also allows you to have like dynamic input spaces, right? So, for example, since you don't have any bounds, there's no notion of like, okay, your X needs to be normalized between like, you know, 50 to 100, right? Like you need to perform normalization based on the x min of 50, x max of 100, or like right, and then later on maybe your bounds change like to like 200 to 400, whatever, right? It doesn't matter because you're representing your x in absolute terms this time. Yeah, and also this regression model allows you to multitask, do multitask prediction. So, for example, you only just need to look at the M and it conditions the model to basically know which regression task it's on. And yeah, like I said, there's no need for tensorization, so you can avoid the need to like compress your x's in terms of like fixed length vectors. And lastly, there's no need for rescaling or normalization, right? So you can avoid a lot of numeric instability issues. And lastly, right, to make things simple, we actually tried this on a very basic encoder decoder, and it's like very small model compared to what people are using these days, right? This is just 200 million parameters. It's definitely not as big as like, 27 billion, 65 billion, whatever parameter models people are using now, which means that yeah. Another thing we did was we did not require the model to be trained on English, right? So actually, we used the model and only started off with a randomly initialized checkpoint, right? So this also keeps it very simple and it avoids any confounding factors. And then yeah, because it's so small, like anybody, even in academia, can try this out. So for example, you just need 8 GPUs for training and 1 GPU for inference. Yeah, before I continue, are there any questions? Okay. Cool. So basically, I'm now going to talk about like one of the possible applications we had on this regressor, right? So basically, I previously worked in the Google Visitor team, so this did a lot of hyperparameter optimization. So that means that basically across Google, we collect everybody's like hyperparameter tuning data, and we store it into this database, right? And for the longest time, we didn't really know what to do with this kind of database. Only until recently, when we realized like it can be used for a lot of like meta learning and black box optimization. But overall, right, the Google Visitor data is like a convenient source of regression data from like AutoML. Some people use it hyperparameter tuning for like chemistry and biology actually, and also people use it for things like in production, like ads and bidding, right? And this is not that super important, but basically what I want to say here is that we collect also a lot of metadata, right? So for example, people like people's tasks, right? We collect in metadata form. So it contains people's like, the title, owner, description, or whatever of someone's hyperparameter tuning task. And so there are a lot of possible transferability sources, right? In one case, like you might have a single user which performs very, very similar experiments, right? That's a one form of transferability. Another case might be like you have different users, but they try similar experiments, right? So, for example, a lot of people, of course, like will train ResNets on C410, right? That's such a common experiment. Another case is like people have similar parameters but different experiments. So, for example, like the name learning rate is actually very common across this data over like all these different experiments. Like someone's tuning a language model or just training a classifier or whatever. And ultimately, their description, like there's a lot of freeform metadata and descriptions, right? Like people sometimes shove in their associated code and file locations. So as a concrete example, here's what it actually looks like, right? And this is actually what the model will see itself as well during training. So for example, your X, right, has some tabular list of like hyperparameters. Your M is basically like this metadata describing what the task looks like, right? Um, Another case is, for example, like another team has been doing a lot of like learning rate scheduling. So, for example, the X will contain hyperparameters for learning rates, and like their scheduling, um, things like that, right? The M also contains things like, okay, what task are they actually doing this on, right? So, for example, the title says something about a transformer. So, yeah, they're gonna do some tuning on transformers. But also like in protein design, the X is basically like very categorical, and then the M is just like something probably not useful here. Um, and yeah, just another example of like an AutoML case for the public use case, right? So a lot of people try to tune their models, and so this X also contains like hyperparameters for I think maybe a CNN or RNN. And then the M also again is like someone's, task. And it contains things like objective names, things like that. Before I go into experiments, are there any other questions?
Just to note that there is a question in the chat.
Oh, cool. This is a question by Richard Cornelius is how sensitive is the performance with respect to the prompt format, i.e. parameter names and their ordering? Um, so I guess you're talking about like the performance of the language model itself. I'll get to that. Basically, that's like in experiments. What we see basically is like actually language models ultimately become just as good as normal traditional regressors, actually. Um, so yeah, let me show that in the later experiments. Okay, so yeah, let me start off with the initial experiment. So the key questions we're gonna answer here, right, regarding like why we actually even train a language model as a regressor in the first place, is number one, can the language model simultaneously regress on multiple tasks, right? Like over different spaces and numeric scales. Number two is like, how is multitask training useful, right? Like, why would we want to train on like basically the data from this separate regression task, like let's say f prime of x, some black box function x prime of x, if we're evaluating on f of x only, right? And lastly, like, right, can we actually fine tune a model, right? Suppose that we pre-train the model over a bunch of like regression tasks. Can we fine tune on a new regression task and like some sort of knowledge transfer can happen to improve your performance, right? So yeah, the first question is simultaneous regression, right? Is the model capable of performing high precision numeric simultaneous regression? And the answer is actually yes, right? So for example, as you can see here, we tried this on a bunch of like synthetic curvy functions. And what you want to note here is that these functions have very different scales, right? So for example, this one function has like scales of 500, but this other function might have scales of like like 75,000 or so, right? But it's interesting how one single model can actually perform this simultaneous regression over all these different skills, and it captures the shape of the synthetic functions over pretty well, right? So that's the first thing. The second thing is right whether it's able to do this on real world objectives, right? So in this case, we have a bunch of like regression tasks where the space is actually very very different, right? So for example, on these first three tasks, you have like four not like double numbers, right? But for another task, it might be like very very hybrid, and it contains things like categorical values and whatever, right? But it's interesting how like this model actually is capable of doing this regression simultaneously over all these different tasks. The key here is like whatever you send for the the metadata, the model like gets conditioned on that to know which task you're on, and so it can predict out all these things, right? So for example, we're predicting out the like the cost of a TPU, right? That's important. Apparently, that's very important inside Google, or we're predicting out the something about ads tuning, right? And this is actually $1 billion question about how well can you predict out like some metric of ads. So this was very interesting. So then another question is like, right, what's the point of multitask training, right? If I only care about my performance on regression tasks with like one regression task, right, with the black box function f of x, then why do I need to train on other regression task data, right? Why is that even useful? So it turns out actually there's some sort of like huge transfer learning going on where as you vary the amount of training data, right, that's the x-axis, even if you train on these tasks like that are not equivalent to what you're evaluating on, the model's regression performance still improves. So the error still decreases over time, right? And so there's some sort of like data scaling law going on here, where as you shove in more and more data, the model just gets much smarter overall, right? Yeah. And so another question people have asked is like basically, so now let's do a apples to apples comparison, right? Where suppose that I only have a single task, right? And maybe it has like 500 points of data, and I'm only going to use this for training for my language model, right? And then let's compare it to another like baseline model, like traditional random forest or Gaussian process or whatever with the same exact amount of data, and let's do an apples to apples comparison and see what the performance is, right? So that's the gray bar here. That's what's called a single task language model, right? Um, and so it turns out that basically, even on the single task case where you have limited data, the language model itself actually is comparable to all these other traditional regressors, right? So actually, the single task performance is actually not that bad, right? This gray bar actually does beat, Gaussian process, random forest, things like that sometimes, right? And you also notice that things like sometimes the gray bar actually even beats an MLP, right? The best regressor actually in this regime. And this happens especially in cases where like the input space is conditional, which means like the input space like is not a fixed dimension, but it has like conditional parameters that like might or might not appear sometimes. So that's that, right? But of course, like since the language model, if you shove in more data, right, the multitask training, if you shove in more data, the model just gets smarter over time. So that's why you see the black bar is always below the gray bar. It's because the model is taking in all this data and getting much smarter. And but also, right, the multitask beats baselines most of the times, right? So for example, this black bar now is basically almost, almost always the best, except for maybe like a slight case. But in general, what you see here is like, even if your language model doesn't win in an apples to apples comparison with traditional aggressors, you can still simply win outright by shoving in just tons and tons of data into this model, right? Even if the data is not exactly the same as your current regression task, right? And so lastly, I want to talk about like, local fine-tuning experiments. So for example, right, this is the classic GPT trick where you can pre-train a model and then hopefully you fine-tune that model on some new task, right? And the hope is that do you see any transferability from the pre-training data, right? So in here, what we want to do was basically say, suppose that we train on like all of the black box optimization regression data up to like so let's train all the data before March 31st, 2023, right? So let's train on all this data before that time date. And then I'm going to perform evaluation on new regression tasks that appeared after that date, right? So therefore, there's no contamination. Training and testing are disjoint, right? And also, let's say like, let's make it slightly harder where let's only care about tasks from distinct users, right? To have like more diversity in the regression tasks. So the question is like, what exactly happens here, right? So for example, in this plot, basically the x-axis is like some unique users like regression tasks, right? So each of these bars is basically some new regression task, and then there's this like blue bar that basically is the error of the model if it's trained using single task regression, whereas this red bar is like if you first pre-train the model over like historic data, and then you fine tune on that new regression task data, right? So the only difference between the blue and the red bar is where is the starting point of the checkpoint, right? Whether it's trained from scratch or a pre-trained checkpoint, right? And so what we see here, right, is interesting, where there are signs of very strong positive transfer, right? So for example, in this section, in this blue, green space here, right, there are cases where the single task regression performance is pretty bad, where it's like the error is very high. But if you look at the performance of like the pre-trained model, then fine tune, right, this is much lower, which means that there's actually like, the pre-trained knowledge of the model carries over to new regression studies, new regression tasks, right? But also there are cases of negative transfer over here where, sometimes like your pre-trained knowledge might be, lead to worse outcomes sometimes. So it's like, it can be up and down, but it does show that like, right, the influence of your pre-training checkpoint, how that affects your overall regression performance later down the line. So that's basically the end of like this initial paper that we had, was basically it validated all these general ideas of like maybe it's possible to just do text-to-text regression over very generic regression data, and here's actually all the mechanisms that might happen here. Before I go on, are there any questions? Z.
Okay. Yeah, I'll directly ask. I saw there's other questions in the comment, but have you compared with multitask GP? Because it seems like multitask LM, like for fair comparisons like, to GP, and maybe we want to have meta learning for Gaussian processes as well, right?
Yeah, this is a good question. Like, I guess, like in the interest of time when we wrote this paper, we didn't. Um, uh, 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 it's like we like the other caveat though is that like a lot of this data is very like heterogeneous. So, for example, the spaces are very like different, right? Um, like I know that you wrote a paper, right, that like allows transferability across like more heterogeneous spaces. But if we're talking about like the traditional notion of like multitask GP, where you have like you still assume that you have like a common X space, and it's just that you're like, your tasks are varying, right? We couldn't even apply that because the data is so heterogeneous. As in like every single regression task has a completely different space. Even if they have the same number of parameters, like the bounds might have changed or whatever. And so like the regular multitask kind of like baselines, have a hard time being applied the moment that like your search space changes even slightly. So that's I guess, yeah, that's I guess our answer to this. Um, uh, yeah.
Yeah, thanks. And Alex, do you wanna
Yeah. So
unmute?
Alex's question is, can you comment on the use of uncertainty in those tasks? All right, good question. So, right, I didn't mention this briefly earlier, but what happens is that the model itself is actually a probabilistic model because we're performing supervised fine tuning, right? Like, uh, we're performing cross entropy loss, and so the model is actually learning distribution. What happened on our side was like we found that in the case of regression, um, we found that if you take the median of the samples, then that was actually the best point-wise output that we can give. Um, as for like actual uncertainty, uh, we do have later papers that actually say like, okay, the model actually is capable of actually regressing and performing, not regressing, like performing um, like distribution estimation, like on any form of like distribution, like it's capable of universal distribution density estimation. That's the right word. Yeah. Um, so yeah, hope that answers the question. Like there are a lot of future papers that we actually wrote on this. I just didn't have time to present it now. But they established like the theoretical parts around the density estimation of language models actually. Um, I guess another question is by Natalie is, can you talk a little bit more about single task versus multitask for the protein design application? Um, yeah, so okay, so the first thing is that this data is just like dirtily collected from a lot of users, right? So like I don't actually know exactly what the protein design was, but we did have like people within this team, specific protein design team, where they tried a lot of like different protein optimization tasks, and it's basically just like this one protein design task has like 60 categorical parameters, right? That's one task. Another task has like 40 categorical parameters, and so forth, right? Just that's basically what the task looks like. It's just like different categorical black box functions, right? And so when we did the training over all of those, we actually did see some form of uh, like transferability, right? As you can see here, like protein design, the black bar is still below the gray bar. So like apparently even on that kind of super categorical task, there's some sort of transferability happening there. That's all I know about protein design, what we call protein design. Yeah. Um, I guess another question by Si Wang is, does the model generalize the task unseen during training time? Okay, so this is a nuanced question. So the key difference between our work and what you normally might expect is our work is not in context learning, right? It's basically just like one single model, and it assumes that you can only fit one example on the context window. It's just that the learning happens inside the weights, right? Like the regression, like the model absorbs in new regression data on the weight side rather than in context learning. And they're like, both pros and cons to this. The pros for this is that it allows you to have very flexible X's, right? Your X now can be like 32,000 tokens long. It can be 1 million tokens long. Who knows, right? And so it allows a lot of flexibility in representing your X's. You don't need to compress it in order to make in-context learning work. That's yeah. So how the model actually performs generalization tasks unseen during training time, like, right, you still have to, when you see a new regression task, you still have to have the model train over the new task like training data, right? So that in that case, for our situation, we have to perform gradient-based updates, right? So local like gradient-based updates, maybe like you can use LoRa in order to absorb the new task training data, right? So that's how we're actually doing it. So that's the subtlety between this and in context learning, which is able to perform like new task generalization, but in a different way. I guess another question by Shifan Zhao is, have you ever tried model on time series data? Right. So that's actually relevant to what I just said earlier. Is that time series is a bit inherently in context, right? Like time series, that's right. That's the right. Time series, generally speaking, is very in context. So basically, like this kind of method is not exactly targeted for time series, but it is possible to actually do this in time series. How you do this, right, is basically you just say like, if you have time series and say like, okay, here's some metric at time t equals 0, here's some other metric value at time t equals 1, and so forth, right? You can actually turn all of those time step examples and treat it as like a normal flat regression task, right? Where like you now have x, y pairs as well. It's just your x is basically like your time. X contains like your time parameter, right? So you can absorb that into the model as well. And we haven't tried this for time series, but like I do think with enough like if you try this hard enough, I do think the model is capable of performing some form of time series modeling as well in that sense. Yeah, I hope that answers everybody's questions. Okay, cool. So yeah, I guess like let me just move forward and talk about more like more broad like conclusions here. So right, like so for example, right, like there are future applications that we do think this can be applied to, and we're actually applying this in Google. So for example, okay, so for example, one case, right, inside Google, for example, is like latency prediction, right? Like some people are really want to figure out like given a compilation graph of like your neural network, you want to predict out the latency, because if you predict out the latency, you can actually reduce the latency of compilation, and this gives you a lot of savings, right? Especially over LLMs, right? And so this task basically like had a very domain specific baseline where they use a bunch of like graph neural networks in order to do this, right? Because the data itself is not very, it's not tabular, right? It consists of like computation graphs, right? And so the interesting thing was that, right, if you convert that to text and we apply it to like our case, right, text-to-text regression, this is what it actually looks like, where basically you have this like very complicated graph, but if you just JSON it, right, and it just looks like a bunch of strings. And as it turns out, the model is smart enough to perform regression on that. And like it just figures, for some reason the model just like is so smart after training that it figures out like how to like look at the specific features that actually matter, and then predict out the y value here, right? And even more broadly, right, how this relates to general like AutoML like AI scientist efforts is that maybe it's possible to predict out um, the outcomes of experiments from like entire code bases, right? Basically, what you're trying to say is instead of just having like compressing your regression tasks into a tabular format, it's possible to actually represent fully your regression task in terms of like just overall general text, right? And so maybe one day it's possible to actually look at someone's code base, see what the experiments they launched, and predict out the outcome of that experiment, right? And so I want to just emphasize the point that this text-to-text regression can actually be very, it's powerful, but also simple and scalable, right? The input can be anything like configuration files, graphs, contours, language, whatever, right? And more broadly, there's been a lot of work on like, generalizing this kind of idea, right? So for example, your targets are no longer just floats, but can be language outcomes. And so where like people have been doing this for, neuroscience experiments where like they take a language model and then fine tune it on language model, like neuroscience experiments where the targets are like scientific outcomes, but in string format. They actually managed to do this. And more broadly, this alludes to this idea that like language models actually are capable of this sort of dynamics prediction, right? It can actually be able to use, it can actually be used for modeling like the dynamics of certain systems, right? You can see that like people have been doing this for video to video, like basically image to image tokens already. But maybe it's possible to just do this generically for any string representations, right? And well, there's a lot of open questions still, right? Like I covered regression in this talk, but for example, it's still unclear how you do in context optimization very well with language models. Like, right, regression has been a lot easier for us to actually do research on because verification is easier than generation. But in a lot of optimization settings, right, you want the LM to know like how to do exploitation, very well. That's actually very unexplored currently. Yeah. And lastly, right, this is more basically about like in general, this sort of work is trying to target sort of like the AGI optimization, where maybe one day you can have like a language model that can take in any different uh, like data formats, right? Not just like tabular regression anymore, uh, but basically, like code, data sets, figures, whatever, right? And so that's the much more broad vision we have for this work. But with that, like for the interest of time, like thank you. I let me conclude on that. Yeah.
So I'd like to also conclude sort of the talk part by thanking Richard for today's talk. And we're going to now move on to the question and answer discussion period. And I just wanted to comment on that there will be a part of that that is live streamed. And then there will additionally be a part that after we turn off the live stream for anybody that feels kind of uncomfortable asking questions sort of in public, that we'll have an opportunity for that as well. And so if you have any questions, you can use the raise your hand button or write them into the chat. I also wanted to comment one more thing, which is that for any of the viewers on YouTube who are interested in participating in these seminars, our website is gp-seminar-series.github.io, so feel free to sort of go on there, sign up, and check out the remaining lineup of the talks. And in the meantime, I'm going to hand it back to Richard for kind of any further questions, although we've had a bunch of questions during the talk. So, but yeah, let me hand it back. Thanks so much.
Yeah. So yeah. By the way, like I know there was quite a few questions also like uncertainty estimates, things like that. Like, in interest of time, I kind of made this like very compressed, but like we did have a lot of ablation papers where basically we checked exactly like how this language model is actually performing regression, both on the like the input representation and the output representation, right? So, for example, as for the inputs, we checked like basically like um, is the model actually capable of learning like sort of Lipschitz continuity, basically? And so we found on the at least the embedding side was like is actually it is learning Lipschitz continuity, as in like the model like if you embed two inputs that generally are very close to each other in like regular traditional space, then the embedding space they're actually very similar as well. So that's number one. But also we check like for example, is this actually like principled to sort of um, perform uh, like perform regression using cross entropy as a loss rather than mean squared error. And it turns out that actually it is completely fine. Like we had a lot of results where we said basically like we found that this model, this decoder model actually even has a lot of benefits over mean squared error value heads, where it's capable of actually modeling like very weird functions that have like unbounded unbounded like values, things like that. So like it can actually model the hyperbolic function as well. It can match uh, in general, it can match like pointwise value heads. And overall, it's like, you get density estimation for free, where you can actually estimate, do density estimation, all these weird curves that are multimodal. So like we have all these other results. In the interest of time, I didn't really show them. But we've sort of like de-risked this idea of like, you can actually use language models and all of its components for regression, and everything's fine. Oh, by the way, there's a new question by Siwang. Is there any visualization example on the model's prediction? Like when you swipe learning rates, does the model's prediction of the accuracy shows U curve? Well, so I mean, I guess like yeah, I just sort of show that like on the output side, it's capable of modeling like distributions, right? On if you're talking about like normal regression, I mean, yeah. So these are like visualizations, right? Although this is on toy task. Um, like as for the original visualization on the curvy functions, right? We have these ones already, which is like the if you can see here, the blue line is like the normal curvy function, and the model is outputting sample predictions, and it's like matching the curvature of the function pretty well. Yeah, I hope that answers the question.
All right. And so I'm going to take this opportunity now to conclude the live stream. And before that, I want to just thank all of our listeners on YouTube for joining us today, and just remind everybody that we have another virtual seminar coming up next week. So you can check out the schedule on our website and